Hey everyone. So today we are getting into those molecular shapes, talking about why do molecules get into the certain shapes that they get into. And if you remember from last year, that is called VSEPR. Okay, VSEPR. We are actually in chapter 9. Okay, so this is the beginning of chapter 9. So let's just go ahead and retitle this as chapter 9. Okay, which is molecular geometry. Pretty much. Geometry. Your chemistry teacher can spell. Okay, so chapter 9 is molecular geometry, valence shell theory, okay, which is, again, what I like to call VSEPR. So we'll talk about those different shapes that we discussed last year. Okay, we'll talk about some hybridization, which is brand new, and we'll talk about sigma and pi bonds, which is also brand new. VSEPR, what is that? That is valence shell electron pair repulsion. It's just pretty much, since the electrons want to be as far away from each other as possible, and they form a compound, what kind of shape are they going to take on? Okay, so reference this guy. I attached this below the video. We're going to be referencing this guy a lot. So make sure you have that in front of you or on a tab separated so that you can see what is going on. The first thing I want you to know is we gotta be able to identify domains, okay? Electron domains are just a grouping of electrons. So it could be a lone pair, a single, double, or triple bond. So if we look at this, lone pair counts as a domain. Single bond counts as a domain. This is how I look after senior guys' lab sometimes. A double bond counts as a domain, okay? And a triple bond counts as a domain. So each bonding pair or electron pair is a domain. Some of you guys like to look at this triple bond and say, hey, that's 3 domains. Nope, it's just one domain. This is one domain, this is one domain, this is one domain, and this is one domain. Okay, so if we were to look at something like H2O, and I say, how many domains are around that central atom? So the central atom is oxygen. How many domains are around that central atom? 1, 2, 3, and 4. 4 domains. Okay, that becomes important later on, especially when we're talking about our shapes here. Okay, when we're looking at these shapes, okay, you're only going to go to the 4 domains. We don't go lower than this. You can go ahead and brush up on this if you want to. Every now and then the AP exam will throw one of these at you, but they don't expect you to memorize all of these, okay? But these first 3 rows, they definitely do. So let's just go ahead and let's go through each of those shapes. So, first shape you might see quite frequently has, I'll give you an example, is Beryllium Chloride, okay? How many domains does beryllium chloride have around that central atom? When I say domains, it's usually just around the central atom, okay? But how many are there? Just 2, okay? And that's going to form a linear molecular geometry. I will ask you, what is the molecular geometry? Linear, okay? It's because it's in a straight line. And then another thing I might ask you is, what is the bond angle? Right, if those bonds are as far away from each other as possible, think of it in 3D, it'll be 180 degrees. Okay? So linear, 180 degrees. And let's just state if this is polar or non-polar while we're at it. There's no lone pairs around the central atom, okay? And both of these guys are the same, so they're going to pull with the same strength on those electrons, and so it's going to be non-polar. Okay? Good example of this. Beryllium chloride, if you were to look at it in 3D, it would look something like this. Okay? Nice straight line, no matter how you look at it. Those electron bonds are going to be as far away from one another as possible, right? So it makes it a nice 180 degree angle. Another place you might see this is in carbon dioxide. Right? How many domains are around that central carbon atom? Once again, just 2, so it's linear. So here's another example. of a linear compound, right? It's only got 2 domains, 2 electrons there, so those electron bonds are going to get as far away from each other as possible and make a nice linear shape. Next domains we're going to get into, okay, are 3 domains. So our examples of this, we'll go with boron trichloride, and then our other third domain, let's see, what am I going to go with? Let's go with silicon dichloride. Okay, so these are ones that have 3 domains. Okay, 1, 2, 3 domains. 1, 2, 3 domains. These guys, okay, are always going to have a bond angle of 120. If you have 2 domains, like in our last example with CO2 and beryllium chloride, those were 180 degrees. But since these ones have 3 domains, they're always 120 degrees. Okay, 120 degrees. If we look at this guy, it's got 3 atoms around it. Okay, no lone pairs. So it's going to be that first shape of trigonal planar. Okay, trigonal because there's 3 atoms. Okay, it's going to say trigonal because there's 3 atoms, and planar is because they're all on the same plane. So this is a trigonal planar molecule. The furthest they could get away from each other is 120 degrees. So if you looked at it sideways, I'm trying to match this camera here, it's on one plane. That's why it's called trigonal planar. Okay, 3, trigonal, it's on one plane, planar. So trigonal planar. All right, and this molecule just happens to be nonpolar. Okay, it won't be the case for every trigonal planar one, but this one is nonpolar. This guy, he's got 3 domains, but he is no longer trigonal planar. He doesn't have 3 atoms, right? So can't be trigonal. What this guy is bent. Bent. Those atoms bent downward because of that lone pair on that central atom, so it causes it to be bent. And then that guy would end up being polar because he's got a lone pair on the central atom. So the only thing that are the same about these, that are the same about those two, is that they have 3 domains, so that gives them 120 degrees, but the shapes can be different. You could run into trigonal planar, or you could run into bent. The next one that I'm going to talk about, which we see a lot, are our 4 domain ones. I'm going to erase this title as well. So we could have something that looks like this. We could have something that looks like this. And we could have something that looks like this. Okay? Once again, they all have the same domains, right? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. They all have 4 domains. So since they have 4 domains, they're all going to have the same bond angle, which I say is our favorite radio station, 109.5. Tetrahedral 109.5. So if you see 4 domains, you're thinking 109.5. 3 domains, 120. 2 domains, 180 degrees for a bond angle. Thing that's different is the molecular geometry. This guy has 4 atoms around it, so it is a tetrahedral. Okay? Tetrahedral. Tetra, meaning 4. That's why Tetris is called Tetris. All those blocks are made out of 4 squares, right? That square block is made out of 4 squares. The straight line is made out of 4 squares. The L's are made out of 4 squares. That's not a square, but you just know what I mean. Right? They're all made out of 4 squares. That's why they call it Tetris. The Russians created that for you so that you could play that mindlessly for hours and hours. I thank them for that. So tetrahedral, 4, and if you looked at it in 3D, when I draw it on the board, right, it looks like it's flat. That's not how it is in real life. It actually looks like this, and that's where you get that 109.5 bond angle, okay? I know you're thinking, wait, 360 divided by 4, shouldn't that be 90? No, remember, it's in 3D. These are 109.5 bond angles, okay, your favorite radio station. So tetrahedral, because there's 4. This one, it's got 4 domains, but it's only got 3 atoms, so this makes it trigonal, but it's no longer on a plane. Okay? It's no longer on a plane because that lone pair pushed those atoms down. So it pushes those 3 atoms downward into a nice pyramid shape, so they call this trigonal pyramid. How nice is that? So trigonal planar used to be this because it was on one plane, right? 3, trigonal planar. But now since that lone pair came in, it pushed those atoms downward into a into a pyramid shape. So now it's trigonal pyramid. Okay? So this was trigonal planar, but now since that lone pair got in and they had to move away, it becomes trigonal pyramid. All right? This is nonpolar, by the way. All atoms are the same. This is polar because there's a lone pair on that central atom. And the last one, 4 domains, 109.5, but it's kind of similar to our 3-domain one from previously. It is bent. Okay, those 2 atoms, or 2 lone pairs, sorry, push those atoms down, and you get something that looks a little bit, well, I had a water molecule sitting here somewhere, but that's okay. It looks a little something like, I could improvise this, okay, with a lone pair on the end. So it forces those atoms down, giving it a nice bent shape. Bent. Okay? So, again, you could see all different types of these molecular geometries. Like with trigonal planar. Okay? I drew trigonal planar like BH3 previously. But it could be something with a double bond. It could be something like this as well. Alright? That's still trigonal planar. Okay? 3 domains, 120. Okay? 3 atoms, 1 plane, trigonal planar. Some of you, what you'll do is you'll make this mistake. Is you might do something like this. And say, hey, I drew it linear, so it must be linear. No, guys, it's bent, right? When you're looking at it like, as you drew it, you're looking at it like that, right? So yeah, it looks linear from this angle, but remember, it's in 3D. Those lone pairs push it down and make it bent. So make sure you're counting your domains, 4 domains, 2 atoms, 2 lone pairs. It's got to be bent. All right? It's got to be bent. Let's go ahead and let's get into our next thing. So make sure you have those 4 memorized. Make sure you got your bond angles down. Make sure you got your polarities down. Now let's talk about hybridization. Hybridization. All hybridization is it's just the mixing of orbitals. Okay, it's kind of like when you take a poodle and a Labrador and you get a Labradoodle. Well, this isn't as cute or as fun. This is mixing orbitals. So it's like taking an s orbital and we're mixing it with a p orbital, right, which looks like a which looks like a dumbbell or a figure 8, and they will just make a weird looking orbital like that. Okay, that's hybridization. And the main thing you have to do is identify the type of hybridization around a central atom. Okay, so here is what you need to know. If you have, say we have domains on one side and hybridization on the right side. Okay, if you have, you'll never have just one domain. If you have 2 domains, your hybridization is SP. Okay, Okay, it's a mix of a s orbital and a p orbital. If you have 3 domains, okay, your hybridization is sp2. Maybe you're starting to see a trend here, okay? If I have 4 domains, my hybridization is sp3. Now here's where I might throw you off. If I have 5 domains, maybe you could guess it. Okay, if I have 5 domains, my hybridization is sp3d. And the last one you'll see is 6, and it is sp3d2. Okay, we don't get any higher than that. Theoretically you can, but scientists don't even know if these hybridizations even exist. Okay, these are just kind of like theories that they'd like you to know. Super simple, easy trick to it. Okay, when you're looking at these, you have 2 domains. If you count up all the exponents, 1 and 1, it's 2. You have 3 domains, right? You count up all the exponents, 1, 2, 3, you got 3. Right? 4 domains, all the exponents, 4. 5 domains, count up all the 5 exponents, 6. Count up all the exponents, 6. And just remember that it will max out at 3 for the p orbital. That's just because p only has 3 orientations, right? It's only got the sideways, the x, the y, and the z orientation. So that's why it stops at sp3, and then d just stops at 2 because they don't think there's any hybridizations past sp3d2. Okay, so if we were, say, to look at something like, let's go with CH4, our basic CH4. How many domains are around that CH4? 4, right? 1, 2, 3, 4. So that means our hybridization around that central atom is sp. So the question will be, what's the hybridization around the central atom of CH4? sp3. You base it off the domains, okay? I don't ever want to see a sp4 because that doesn't exist. Okay, I don't ever want to see a s because that doesn't exist. Just make sure you're counting the domains and following your kind of your intuitiveness with orbitals and orientations to help you out. Okay, say I was looking at CO2 and I just want the hybridization around the central atom, right? How many domains are around CO2? 2. 1, 2. So my hybridization is just sp. Okay? 1 for the first domain and 1 for the second domain, sp. Let's give you a trickier one here. Okay, what is the hybridization in the Xenon tetrafluoride molecule? I look at that, I count how many domains are around the xenon. 1, 2, 3, 4, 5, 6. 6 domains, right? S counts for 1. The max I could put in my P is 3, so I have 4 so far. sp3, D2. Okay, and that's 6, right? 1 S, 3 P's, 2 D's gives me 6 domains. So sp3d2. Remember, the max S can have is 1, the max P can have is 3, and then we don't get higher than 2 for D. So make sure you got that down for hybridization. Right? That's hybridization, guys. One more thing, sigma and pi bonds. Okay, so sigma, which is given by that sign, which kind of looks like a side view of a whistle. Sigma and you all know pi bonds. Okay? Sigma and pi bonds. So what are these? Really easy, okay? Every first bond in a domain is a sigma bond. Okay, so every first bond in a domain is a sigma bond. Every bond after that is a pi bond. Okay? Is a pi pond. Wish they had pi ponds. Sounds delicious, right? Just dive into some blueberry. Anyway, so every sigma bond, every first bond is a sigma. Every other bond, like a double bond or a triple bond, is a pi bond. So let's talk about that. So if I look at a single bond, okay, remember any first bond is a sigma. So that single bond just has a sigma bond in it. If I look at a double bond, okay, the first bond, which it could be the top one or the bottom one. It doesn't matter because we don't really know which one came first. As long as we designate one of them as sigma, like this guy, every bond after that is going to be a pi. So we'll call that top one the pi bond. Triple bonds, right? Again, it doesn't matter which one you call the sigma bond, okay? Just know that only the first one could be a sigma bond. So only one of them could be a sigma bond. So that'll be sigma, and then that'll be pi. So 2 pi, 1 sigma in a triple bond, sigma pi for a double bond, and sigma for a single bond. So let's go ahead and let's look at some real world examples for this. Let's go with something like this guy. I don't know why I put 4 there. You'll only see 5. If that. Yeah. Okay. Or 4 if that. So what we're going to do is I want you to state or label all the sigma and the pi bonds, okay? Remember, any first bond in a domain is a sigma. So in this domain, that single bond is just a sigma. In this domain, that single bond is just a sigma. In this domain, that first bond is just a sigma. Okay, so any single bond you see is always going to be a sigma bond. But that double bond up top, okay, remember only the first one is a sigma bond, and then everything after that is a pi. So in this example, we have 4 sigmas and 1 pi bond. Okay, that's usually what they ask you. How many sigma and pi bonds are in this compound or in this molecule? All right, something like that. Let's go to another example. HCN. How many sigma bonds and pi bonds are in HCN? Okay. I'm looking at that guy, right? I'm looking at the domains. I have 2 domains here. Any single bond is a sigma bond, right? Because the first bond in a domain is a sigma bond. And for this triple bond, it doesn't matter which one, okay? Let's just say that top one is the sigma bond, but then every other bond after that first bond's got to be a pi. So pi, pi, so 2 sigma, 2 pi bonds. Okay, be ready for that. They like to hit you with that in organic chemistry as well. All right, just remember every first bond is a sigma, everyone after that is a pi in a certain domain. That is it for molecular geometry. Make sure that you're studying that paper and you know your shapes, you know your bond angles, you know your polarities, we know our hybridizations, and we know our sigma and pi bonds. That's it, guys. Have a great day.